So welcome everybody to the series of Sharma seminars on functional programming. We've got a seminar every week for you for the next 8 weeks, and a very exciting program. And I'm delighted that Simon agreed to kick off the series for us. Simon, of course, is a distinguished researcher at Microsoft Research, a fellow of the Royal Society, the man behind the Glasgow Haskell compiler. He needs no introduction, really. So what we're going to do is we're going to leave the chat open, but we're not going to use it for questions. And if you would like to ask Simon a question during the talk, please raise your hand, and then Simon will respond and we will unmute you so that you can talk to him. Otherwise, attendees are muted by default. And if you would like to ask a question at the end of the meeting, then we can use the Q&A that Zoom provides. And if you put questions there, you can also upvote them. But to begin with, we'll see whether holding hands up and asking questions during the talk works. So, Simon, with that, over to you.
All right. Thank you, John. Welcome to everybody. It's very nice to meet so many of you at one time. This is a story of a long quest that I've personally been engaged in for at least a decade and a half, and has been actually going on for rather longer than that. Sometimes in research, you push on a door and it swings open unexpectedly, and sometimes it seems to be open and you keep pushing and it keeps shutting on your fingers, and that's rather what's happened to this. So this talk is really about a little step forward that we've managed to make recently, and I hope to give you a pretty clear, intuitive idea of what the problem is, what our solution is, and a little bit of the technical detail about how it all works. So let's kick off. Polymorphism, the glory of ML-style polymorphism is that you can function that works on arguments of many types. So here's reverse. It has type for P, list of P to list of P, and it will work on lists of booleans and list of numbers and list of booleans. So one function, one blob of machine code, many types. That's the glory of ML-style polymorphism. Now, what goes wrong with that? Well, hang on. So at a particular call, we're then instantiating reverse at different types, and I'm going to use this at notation for doing that. So I'll say that at the call on reverse on a list of true and false, I'm instantiating reverse at bool. On list 1, 2, 3, 4, 5, I'm instantiating it int, and on list of booleans, I'm instantiating it list of booleans. So another way to think of instantiation is this: that you can these at things you can actually write explicitly in GHC's form of Haskell with a little at sign in front, and you can imagine that the at bool thing is like an extra argument to reverse that says how to instantiate that initial for all p. So I hope you can see the laser pointer. Here's the for all p at the front of reversed, and I'm going to the at bool instantiates that p, so the remaining part of the type is list of bool to list of bool. If I instantiate it with int, the remaining part of the type is list of int to list of int. So I hope that should be straightforward. I'm going to write quite a lot of these at signs in the rest of the talk to come. So one of the key things about instantiating polymorphic types with lists of different applying reverse to lists of different types is that functions are first-class types. So here I've got a list that contains not and id. Here's the identity function. Those two functions in a list, and I can call reverse on that list. And here's how I do it. I don't need to write this stuff in red. The compiler will fill it in for me. I'm allowed to write this stuff in red, and then. So what happens here? That's right. So I'm instantiating reverse at type bool arrow bool, because that's the type of P. I'm a bit busy, darling. And then, of course, I have to remember that in the argument, in the components of the list here, not an ID. Not is not polymorphic. Look, it has type bool arrow bool. But ID is polymorphic, so it needs a type argument. Here's this at bool. So I'm actually instantiating ID at the type bool. To make it work in this particular context. So again, these at things can be optionally be written explicitly in GHC's version of Haskell, but usually you just leave them out, and all of this happens behind the scenes. The glory of polymorphism, you can call a single polymorphic function at lots of different types, and I'm just using this at notation to go for explicit instantiation. So now, in traditional Damas-Milner kind of type inference for ML, the for alls can only appear at the outermost level of a let-bound function. So here's three functions. Well, F1 here has its for alls at the top, right? For all P, list of P to list of P. F2 has a sort of nested for all to the left of an arrow. F3 has a nested for all to the right of an arrow, and F4 has a nested for all inside a list. And none of those are allowed in traditional Damas-Milner kind of type inference. So what that means is that for all types, unlike arrow types, are not first class. Right? So another way to say it is we can't instantiate reverse with a for all type. We can instantiate reverse at bool, we can instantiate reverse at AROA, but we cannot instantiate reverse at for all A, AROA. And I'm going to use the word impredicativity to describe this idea of instantiating a polymorphic function with a polymorphic type. That is to say, instantiate that a type variable can range over any type, including a for all. And Damas-Milner really doesn't allow that at all, and that's what this talk is about. So but having said that, I'm using impredicativity in this way specifically, but this isn't the only way people use it. It's a slightly ambiguous term. I'm using it to mean that for a predicative system, type variables range over monotypes, that is with no for alls. In an impredicative system, type variables can range over any type, including types with for alls. And the difficulty there is to do with type inference. Now, in dependent type theory, predicative usually means that there's a stratified universe of types. And impredicative means we don't have such a stratified universe, and in particular, type has kind type. And the difficulty with impredicativity there is that if you're not careful, you get into logical inconsistency, and you really can't have that at all in a language about of full-on dependent type theory. So you really have to be very careful with impredicativity, with that form of impredicativity. But I'm going to use it today just in the sense of type variables can range over polymorphic types. So Damas-Milner then, remember, for alls only at the top level of a let-bound function. So we found a way to go quite significantly beyond that without going to impredicativity by using higher rank types. So in higher rank types, you can have for alls at the outermost level of a let-bound function and or to the left and right of a function arrow. So here F2 and F3 become legal, F4 remains illegal. Okay, so it's still predicative in the sense that type variables can only range over monotypes, but higher rank types give you a lot more expressiveness. So this has been in GHC for many years, nearly two decades, I think. Here's some examples. Run ST, which does encapsulated state, very significant step that we took really some time ago, needs a for all to the left of an arrow. There's a whole series of papers about scrap your boilerplate in which there's this function generic T, I just picked out one out of many, which is short for all A, data A to A. And we can have functions that take a generic T to a generic T. So you can see there's a for all to the left and to the right of an arrow. And the famous lens library, the Van Laaren lenses that are popularized by Ed Kmet, particularly, they have also for alls to the left and right of an arrow. So for alls in this higher rank way to the left and right of an arrow, super valuable, and it turned out not all that hard to do. So GHC has had a higher rank for quite a long time, but tantalizingly, still no instantiation of polymorphic type variables with a for all, and that really is a problem, especially when combined with higher rank types. And here is an example. Here's run ST, the function I mentioned earlier, with its type here with a for all to the left of an arrow. And here's $. Now, $, is a Haskell function that is just short for function application. So it has the type for all AB, arrow B to arrow B. It's a pretty funny function, but sometimes you want a name for the apply function, and here it is. And indeed, people, instead of writing run ST applied to some expression or identifier ST here, whose type is compatible with run ST, they sometimes write run ST $ST. They usually do that if ST is a compound expression. They don't want to write some parentheses. But lo, you cannot type this. It's so annoying. Why not? Why can't we type this one? It's because we would have to instantiate the type of $, that is apply, with, well, a polytype. Because in this case, the A in the type of $, has to be instantiated with for all S, STS int. Okay, so this is the first time at which something really interesting I think has happened in this talk, is that the use of higher-rank types has forced us, if we are to type this application of dollar, to instantiate with a polymorphic type. Cool. So though that's one way in which high-rank types seem to force you in a direction of wanting impredicative instantiation. And here's another, that you might want to have data structures that contain, well, polymorphic functions. So supposing I had a list of polymorphic functions here, IDs is somehow in the environment with type list of for all A, AROA. What could I do with such a list? Well, I might want to cons something onto it. So I might want to say cons of ID, that is the identity function, to IDs. What could be simpler than to add a polymorphic identity function to the front of a list of polymorphic identity functions? But we can't do this because we would have to instantiate cons. I've written the type of cons here. It has type for all PP to list of P to list of P. I'd have to instantiate that with a, well, polytype. So this is a bit tantalizing, right? No cigar. We're sort of, it's tantalizingly close. And there's been lots of related work to try to find the cigar, the ability to combine pervasive type inference with minimal type annotation, but along with the ability to instantiate polymorphic functions with polymorphic types. And I've written, there's tons of related work that I'm not going to discuss in this talk, it's discussed in the paper, but it does your head in. There are so many acronyms and different language designs, and they're all a compromise balancing the simplicity of the system, the expressiveness of the system, and also how hard the user has to work by adding type annotations to write programs that use this kind of impredicative instantiation. So a quick look, the subject of this talk is just one design point in this space, but I think I feel as if it's a little bit of a breakthrough, at least in my heart, because it strikes a very nice balance between simplicity and expressiveness, particularly simplicity of implementation, as I hope you'll see. Okay. Somebody's asked, isn't the special treatment of dollar built into GHC to make it work for runst? Actually, there is, because this use of runst was so annoying that you could not write runst dollar blah, that we built dollar into GHC's type checker, the single special case of dollar, just for this purpose. That's terrible, but it was so useful that we did it. That tells you how painful it was not to have it. Okay, right. So now I want to say what the problem with impredicative instantiation is. Now, what's the difficulty? Well, let's see. The difficulty with allowing polytypes to range over polytypes is to do with type inference. So here's the simple thing. I'm doing cons ID IDs, and I want to figure out that I've got to instantiate cons with a polymorphic type. What can be so hard about that? Well, to answer that question, I have to give you a quick tutorial in how ordinary classic Damas-Milner style type inference works. And here it is. Imagine here's, I've got a little program in the top right-hand corner of the board. Foo is lambda x's, reverse x's, paired with, that comma is a pair of a tuple, paired with and of x's. So and is a function in Haskell, but I give them the type signatures at the top that just ands together a bunch of booleans. Now, so what do? When we come across the lambda, we don't know what type it is, so we give it just a unification variable, alpha. Alpha is just stands for an as yet unknown type. Then to type check the call reverse x's, I'm going to instantiate reverse, but with what type? That's what we're trying to figure out. So initially we instantiate it with another unification variable, beta, standing for another as yet unknown type. So this occurrence of reverse, this particular occurrence, then has type list of beta to list of beta. That's what happened when I instantiated reverse's type. And now I've got since the argument of reverse has type list of beta, but the actual argument, x's, has type alpha, I can constrain by, as it were, emitting an equality constraint that alpha must be equal to list of beta. Okay, so right, so I'm going to sorry, ordinary Damas-Milner type inference then. Whenever you don't know type, create a unification variable, and then as you type check the program, you emit equality constraints, which you may solve immediately or may delay solving them, that constrain equalities between unification variables. Here we have alpha tilde list of beta, meaning alpha and list of beta must be the same type. Okay, and we've got to figure out how to do that. Now, How are we going to figure out how to do that? Well, let's see, we've also got this other subterm, and x's. And so so since and doesn't have any polymorphism, we don't have to constrain its type, but we can constrain its argument. Its argument has type list of bool. That must be the same as the type of x's, which is alpha. So now we have two equality constraints. Alpha is list of beta, and alpha is list of bool. We just solve those equality constraints, and we can solve them by unification. Standard Robinson unification. That yields a substitution. Alpha must be list of bool, and beta. Oh, no. A typo. Alpha must be list of bool and beta must be bool. No, that's not a typo. That's right. And there's our solution. Now we know what alpha and beta stood for as yet unknown variables, and now they stand for known variables. We know known type. We know exactly what they are. But the trouble with this is this depends critically on the unification variable standing only for monotypes, that is, types with no for-alls, because then the constraints that we emit can be equality constraints and can be solved by Robinson-style unification, and there is a single principal solution to that. There's only one best solution. It just falls apart if unification variables can stand for polytypes, right? So like when I'm trying to instantiate a function in a function call, right, as I said, I instantiate reverse. What if the function was f and it just had type alpha at the moment? Well, alpha might turn out to be a polytype later, but I don't know now how to instantiate it. Also, all the constraints become subsumption constraints. Solving them becomes harder, and worst of all, there's no principal solution to a bunch of subsumption constraints like this. So it turns out the Damas-Milner type inference is kind of delicately balanced on a beautiful sweet spot at which everything works out smoothly and you get principal solutions. And if you try to introduce polytypes try to make unification standard for polytypes, all of that goes out of the window. Okay, so what to do? The trouble is that it looks so easy. It's so tantalizing. Look at this, cons of IDs. How can this be hard, guys? Look, the second argument of this cons is IDs. IDs is known to have type in the environment, has that list of, for all A to A. So if I have, if I'm instantiating cons, which has type for all P to list of P, look, that list of P matches up with that list of IDs. So there's only one thing P could possibly be. Do you see how tantalizing that is? I mean, you look at this, you think, guys, GHC, 20 years of work, how could it possibly think for even a moment before it can decide that the only thing that P can be is for all A to A? Right? That's our goals. So, so here's the main idea. We just want to exploit this idea, and in a way that quite a few other people have tried as well. And so the first thought is, let's treat applications, and this is not unique to this paper, lots of people have thought of this, treat applications as a whole. Notice that it was in the second argument of cons here, the IDs argument, that I looked at to determine this unique instantiation of the instantiation variable P. So I'm going to so here's the basic plan as before. Here in a function call, I'll instantiate the type with unification variables and then type check E1 and type check the arguments against the instantiated arguments of F. But I'm going to change that a little bit by introducing a new step in the middle. So all the orange is new, look, and the white has stayed the same. I'm going backwards and forwards between these slides. The orange stuff is new. So now I picked a particular function here, filter, so that you can remember it's type P to bool, list of P to bool. I'll instantiate filters type with, I'll call them instantiation variables, kappa. Instantiation variables are going to be a bit like unification variables, but I'm going to introduce them temporarily and then get rid of them. So here they are. I'm going to instantiate, at a call, I'll instantiate filters type with instantiation variables kappa to get the instantiated type, K to bool, so kappa to bool, to list of kappa to bool. And then I'm going to take a quick look at the arguments, E1 and E2. So imagine it as being like, I just take, glance aside and look at those arguments E1 and E2 to see if I can figure out what kappa must be. Now, in this case, I know that, this should say filter GIDs. I know that the second argument to filter is IDs, and IDs has type list of A to A. So I can immediately get the kappa must have that type. So by taking a quick sort of look ahead at the arguments, I might be able to figure out what the instantiations are. Then I substitute for all of the instantiation variables. The ones that I've learned about from the quick look, I know what to substitute. Any that I didn't learn anything about, any instantiation variables that I did not learn anything about from the quick look, I just substitute a monomorphic unification variable, and then I'm back to what I had before. So in this particular case, I did learn that kappa is for all A to A. So I replace kappa with for all a to a in the instantiated type of filter, and then I just type check the arguments exactly as before. So this quick look does not replace type checking the arguments. It's just a little bit of look ahead at the arguments. So I hope that makes sense. There's all right, talk more slowly. That's really difficult for me. When do kappa expire exactly? Good question, Arlene. They expire at the end of the orange stuff, right? So this is at a call. At a call site. This is nothing to do with the definition of filter. This is at a call of filter, filter of E1, E2, and instantiate it with kappa, take a quick look at the arguments, substitute the kappas out, and the kappas are gone. What if kappa needs to be equal to two different things? Oh, well, that might be a type error. If it's got to be both int and bool, or two different for all types, it can't be equal to two different types. So that's a program with a type error. Okay. I've got to speak more slowly. Keep telling me that, John.
Okay.
Right. So the thing I want to stress here is that the big picture is quick look simply replaces the step of at a call, instantiate the function with unification variables, with at a call, instantiate the function with types derived from a quick look at the actual arguments. Does it mean the functions have to be fully applied? No. It means take whatever arguments you can see. I will show you that in a bit more formalism later. But basically, in every call, you see however many arguments are just laid out there in the syntactic call. We'll take those ones. Okay. Right. Another thing I want to stress, though, is that everything else is unchanged. Everything else is unchanged. This is very close to ML-style type inference. In all of the rest of type inference, I'm back to ordinary monomorphic unification variables. There's no new form of constraints. With an earlier paper guarded instantiation, we introduced a new form of two new forms of constraints. Actually, it was very tricky, but no new forms of constraints. There are no new forms of types. Other papers have suggested new forms of types. A paper that I was involved in introduced boxy types. No new types. This is ordinary old system F types. No new user-visible type annotations. We have these type applications, to be sure, but they are useful regardless. But there's nothing new related to impredicativity. But very significantly, for me anyway, is that it leaves the rest of the implementation unchanged. GHC has endless other enhancements: type classes, type families, GADTs, functional dependencies, deriving, scope type variables, partial type signatures. I won't read them all out. I had to use a smaller font. None of them are affected at all. So to give you a quantified example of this, here is the line count of GHC's type checker. On the left, before quick look. On the right, after. On the left, 82,804 lines of code. On the right, 83,200 lines of code. This is not a big change as these things go. And almost all of these modules, as you see, are bit for bit identical. Incidentally, 82,000 lines of code is a lot, but this does include probably at least 50% comments and tons of white space as well. Okay. What do we do about instantiating variables not in function positions? Norman, excellent question. For this purposes, as you'll see in the formalism, all variables are in function position. If it's a variable that is not applied to anything, is still treated in the same way, but just with no arguments. I think you'll see that when I get to the formalism. Okay, so I want to say a bit more about what quick look learns from the arguments. So here is a simple case, head. So head, I've given the type in the yellow in the top right-hand corner. I've got the argument, the expected type is list of kappa, because I'm instantiating P with kappa. The expected type, list of kappa. The actual type, list of for all A to A. So there's only one thing kappa can possibly be. Easy. Here's another one. Cons of ID and incs. So incs here is a list of incrementing functions, well, a list of functions of type int, arrow, int. And here again, there's only one thing that kappa can possibly be, looking at the second argument, and the same in the case of the when cons of ID and IDs. So here, let's see. That's right. So here I already went through this. We have to instantiate it for all a AOA. But notice in both of these cases, I'm talking about the second argument. The first argument does not tell us. If I covered up the inks and the IDs, I wouldn't have known how to instantiate cons, right? Because in both, the first argument was the same for both of these. So what's the difference between the first argument and the second argument? The difference is that the first argument has a sort of naked kappa, right? The instantiated argument for cons has a kappa all by itself, whereas in the second argument, the kappa is guarded underneath a list. So this is what shows up in a number of pieces of related work with this, the idea of sort of guarding by a type constructor. So here, the principle is that during quick look, for an argument that corresponds to a naked instantiation variable in the functions type, we're going to learn nothing at all. So going back to the previous slide, we will learn nothing from the first argument of cons. We will only learn something from the second argument of cons. Okay. Eta contraction. I'm going to postpone eta contraction and if IDs is list of alpha, if IDs is list of alpha, then alpha, remember, is a unification variable that can stand only for monotypes. So you cannot ever unify that alpha with for all A to A. Unification variables, just as before, are going to unify only with monotypes. Only these instantiation variables, whose lifetime is very short, are going to unify with polytypes. Okay, let's see. So arrow also is going to be a guarding type constructor. So here is a use of $, that infix application, and I'm going to call it on reverse. But I'm going to call it on reverse with a pretty funny function. So this f has as its first argument a polymorphic function. So f applied to reverse would be fine, but f $ reverse means I have to instantiate $ again with a polytype. So here in the first argument of reverse, I can see that first of all, I instantiate $ at the call of $. I instantiate it with kappa and mu instantiation variables. Then in the first argument, in the quick look, I see that the expected is kappa arrow mu. The actual is, well, it's the type of f, which is an arrow type. And so the only way to solve these is for kappa to be equal to, for all a list of A to list of A. Oh, typo here. It should be for all kappa is for all a list of A to list of A here, and mu isn't. So the important thing for this slide is that arrow behaves as a guarding type constructor. That's very helpful. It gives quick look. It's not essential to the whole idea, but it gives a lot more power to the approach. In particular, it makes $ work well. Okay. Yes, RNTZ, it does mean that treating arguments differently. You'll see that in the formalism too. That a let to the left of an x will be treated differently. I'll show you. Okay, but I still want to get on to what can quick look reasonably do. Now, I said we can look at arguments. We might want to look deeper into the arguments. So here's cons of ID and, in brackets, cons of ID IDs. Oh my. So now we instantiate the outer cons. That's good. So now its second argument has expected list of kappa, and its actual is, oh my, what's the actual? Oh, that's cons ID IDs. So maybe we could recursively quick look into that argument, right? And then instantiate that inner cons in a quick looky kind of way with mu, discover that mu must be for all a list AOA, and then find the type of the inner thing must be list of for all a AOA. Okay, so we can recursively quick look, and you might worry about this, and you'd be right to. So recursive quick look sort of looks deeply inside the arguments, and that's worst case quadratic. After all, that cons, instead of IDs there, I could have had another nested cons and another nested cons. So I could be looking deep into the argument, and all this will happen again when I then move on to the nested argument to type check it. So at worst, this could get expensive. But if it's expensive, it means that the quick look cues or clues are far away, and so maybe they're obscure to the programmer too. So perhaps we should just cut off at some threshold. There's a design choice here. And a good threshold might be 1. We need to experiment and find out. But we might also wonder about amortizing this cost by sort of doing quick look as a pre-pass. And that's very much what Francois and his colleagues did with stratified type inference really some time ago. Okay. Artem asks, can you have IDs in today's Haskell GHC? I thought you can't have fools under type constructors other than arrows. Good question. The whole point of this is we're going to allow fools under type constructors. That's the idea of quick look. We're going to allow that suddenly. Okay. So putting this all together from the arguments, we can actually now do run st of $, right? By taking a quick look at the argument, we need to, and we do need to do a little bit of instantiation. Norman, this speaks to your point that in order to so when we're doing the quick look on $, we instantiate $, with kappa arrow mu, then we got the expected kappa arrow mu from the run st. What's the actual? It's the type of run st. Oh, but that's a for all type, right? So we must instantiate it before doing this quick look business. So that's a little bit like a degenerate version of looking inside the argument. Okay. Is there a nice declarative summary? I'm going to get to the nice declarative summary. Yes, RTN said. Okay, but I'll have to keep going. John, is anything else that I should pause about?
So there's quite a few questions, specific questions down. Might want to quickly take some of these.
Why don't we learn the type for all array from the first argument of, of the cons thing? So that's actually back a few slides. Phil says, why couldn't we learn the polymorphic instantiation just by looking at the first argument of cons? Well, Phil, look at the first argument of cons in the example at the top, cons ID inks. If I didn't show you the inks part, you might be tempted to say, oh, let's instantiate cons at for all AROA. But then the inks argument would not be sufficiently polymorphic. So if we only see the ID part of this application, we don't know how to instantiate cons. I hope that answers the question. Look, the last thing the point I want to make is that I've spoken intuitively about getting information out of the argument. I also want to get information out of the result. So here is foo, which is defined to be single applied to ID. Now foo, I gave a type signature to, right? The user supplied type signature. Single has type for all P arrow list of P, top right-hand corner of the slide. So I said that since the argument isn't guarded, I can't learn anything from the argument. So I don't know how to instantiate P. But actually, I do, because I know the user told me that that the result of this call to single must be list of for all A to A. So an improvement to quick look is, as well as looking at the arguments, if we're in checking mode, that is, if we're pushing types down, and that's crucial to higher rank, we're pushing types down, then we're going to do a quick look style match on the result type as well. So in this example, the result type of the call is list of kappa. Before saying, I don't know anything about kappa, let's replace it with a unification variable. Before that, I'm going to match it with the push down type, list of for all A to A. So there's only one thing that kappa can possibly be. Okay. So that's the end of what quick look is trying to do, to take a quick look at the argument and the result to try to glean information. I'm going to formalize that next. And then I hope some of this will become a little bit more crisp. But let me just quickly go through the principles. And while we're doing that, John can catch up with any questions. So the idea is it's one of these 90-10 things or 80-20 things. We're trying to use simple local reasoning to find out what I'll put in quotes is the only possible instantiation. The thing you look at it and you think, stupid compiler, right? Why can't you see something so obvious? Now, of course, what is obvious will vary between different people. And Of course, this is a design space with different choices, but the meta goal is to try to discover instantiations that are simple to describe, simple to understand, and simple to implement. Remembering that if we get anything that's too complicated in some sense, you can always bail out and use visible type application, those @ signs, to get the more complicated cases. And this design does allow us to have a variety of choices. But I want to take a concrete example of what it means by not trying too hard that showed up in one of the questions. So if there's do you remember I said we're treating applications as a whole? So here's a let in function position of an application. No, quick look is not going to deal with that. It'll only deal with it if you've got a function, if you've got a variable in the head, right? In the head of the application. So yes, you could try harder and deal with let as well, but then what about case and what about a whole lot of other things? So we just elected to do the simplest thing. There's a movable feast here, design choice. Actually, we do let you write an expression with a type signature in the head. So at the bottom of the slide, if you have a function with a type signature, let bound, and you replace that function with its right-hand side annotated with an explicit type signature, and you put that in function position, we'll let you do that. But you could even do without that. Maybe that's a bridge too far. Perhaps just the variable would be fine. It's a design choice, and there's a line you can move here. Okay, but this does work pretty well in practice. Here's a little figure from the paper giving some examples that work pretty well. It's also not Haskell specific. I think all of this would be applicable to pretty much any full-on ML style polymorphism language. And let me stress again, lots of related work. This isn't like a linear spectrum in which one thing is better than anything else. It's a complicated design space. I'm just trying to outline one new point. Okay, so next I want to go on and talk about some formalism, but let's take some other questions first. John, any suggestions?
Yes. So Simon, I don't know if you realize that the questions are ordered by votes in your Q&A window.
9.
So if you scroll up to the top.
To the top, yes, 9. Can we
votes.
write a function blah at the type level? I don't propose to answer that. I'm not talking about type level reasoning of type classes. No, I propose to not take that question. What exactly is quick about the quick look? Andrew, it's just that it's a little look ahead at the argument that does really not very much work on the argument and bails out quickly. It might even bail out if the argument isn't just a variable or isn't a simple application at a simple nested depth. So it's meant to be fast. It's not full-on type checking. I think, again, I'm going to show you this in the type system. What happens if the head of an application, typing is not stable under eta contraction. No, it is not stable under eta contraction. That's right. Actually, yes, have a look at the paper. There's quite a bit about eta contraction in the paper, but I think it's, but actually, if you eta contract something and the argument of the eta was not, if the lambda had a type annotation, well then, eta contraction, we would not be stable under eta contraction because a type annotation might have a polytype in it, the user-written type annotation. If the expanded version did not have a type annotation, it would have to have a monotype. So there again, so then I think it maybe is stable under eta contraction. My co-authors can think about that. I'm not sure I can do that on the fly. What happens if the head symbol of an application is not a function, but a variable of which the type itself is not known? Good question. So in Damas-Milner type inference, let-bound variables, their polymorphism is always known, right? You can say a let-bound variable might have function for all it might have something like A to alpha. Alpha might not be known, but you know exactly where all the polymorphism is. So its polymorphic structure is completely known. And that's true in quick look as well. For a lambda-bound variable, well then its type would just be a unification variable or perhaps a monotype, and there'll be no instantiation to do. We'll only instantiate polytypes. Would cons ID $IDs cause any problems? That's a good question. We'd have to quick look on ID and ID. I think it would be fine, but that's a good question that would actually mean you need to look at the type system. the more complicated the example, the less obvious. I mean, because now you've got to polymorphically instantiate both dollar and cons. Good, excellent question though. When do kappas expire? I think I did answer that, namely immediately after quick look, before you start looking at the arguments. Did I answer that? I think I did. Would the introduction of dependent types solve the problem by expressing ID as ID? Oh, where I don't think I can parse that question. But certainly in GHC today, you can write explicit arguments, then with impredicative types, they can be polytypes, and then everything will work out fine. So if you supply explicit instantiation, including explicit instantiation with polytypes, you're fine. I really want to do a little bit about formalism because I promised that I would finish before 55. I've got 9 minutes. Let me show you. I just want to show you a bit of formalism so you can read it in the paper. Look, here is the language. It's very, very small language, and I'm showing you the syntax of expressions just to stress to you that it treats applications as a whole. So here in the expression language, E is an expression. So one form of expression is an application H to arguments pi1 to pi n. The pi arguments are either sigmas, that is types, that's for explicit type application with those @ signs in concrete syntax, or ordinary value arguments. And H, the head of an application, can either be a variable or an expression with a type signature, or an arbitrary expression. And quick look is not going to take special. So that you can have an arbitrary expression then, but then quick look won't take account. Or it can, and we can also have lambdas, of course. Now here's the type system. I'm not going to show you this in detail for bidirectional type checking of these terms. And I'm just going to have a look at abs. The arrow here is up arrow if we're doing inference, and down arrow if we're doing checking. So you see for lambda, for inference, I can infer that the type of the variable x must be tau. Tau stands for monotypes, no for alls. For down arrow, if I'm pushing down a type sigma A arrow sigma R, then x gets to have the push down polytype. So that's the way these arrows work. I'm not going to pause there because it's not relevant to this talk so much. Look at the application rule there. Application rule for a head to a set of arguments. What does it do? Well, here it is blown up. First of all, we're going to infer the type of the head. What does that mean? Well, let's go back a slide. That's at the bottom here. Inferring the type of the head. If the head is a variable, we know what type it has. Look it up in the environment. If it's an expression with an explicit type signature, we know what it is. It's the signature. Anything else, we're just going to infer it, and that means we'll get a row type. Now, a row type is a type with no for alls at the top. That's all you need to know for this talk. A row type has no for alls at the top. So this rule will only get an interesting polytype, that is one that can be instantiated, for variables and expressions with signatures, the head. Then what are we going to do? We're going to instantiate with this instantiation judgment. We instantiate the function type on those arguments to get phi bar, that is one type for each of the supplied arguments. And then you can see that later we're going to type check down here. We type check each of the arguments against the phi's. That's what happens at the bottom. But of course, instantiation also returns the result type row R, and we're going to make sure that the row R is the things returned by row. Now, finally, what's this theta business? Well, do you remember that in quick look, I'm going to first instantiate with instantiation variables and do quick look. All of that is going to be inside turnstile inst. But then I'm going to say any of the instantiation variables that I didn't get rid of by quick look, I'm going to turn into ordinary unification variables. And that's what this, this theta is doing. Now here we're in a declarative system in which we don't have unification variables. We just have taus invented magically out of thin air. Look, in this lambda rule, I didn't say for inferring lambdas, I didn't say, oh, x has type alpha, a unification variable. Instead, I said x has type tau, invented out of thin air. That's how declarative type systems work, as opposed to type inference algorithms. And it's the same here in this rule. Theta is invented out of thin air, and it is all the taus for the instantiation variables that we have not yet figured out. FIV stands for free instantiation variables. Okay. Okay, yes. Oh, by the way, yes, you can, on my homepage under the publications tab, you can see the draft paper, and so you can see all of these rules if you want. Okay, so what about this instantiation judgment? So far, I'm not actually going to do, I'm going to show you what it looks like without quick look. So what does it do? Well, it takes, this instantiation judgment takes the type of the function and the arguments and returns the types of all the arguments and the result type. And it just recursively invokes this turnstile I judgment, which does the work. And it's here. I'm not going to go through it at length because I'm going to show you it again in quick look form. But suffice it to say that it accounts for visible type application and ordinary implicit instantiation as well. And I think I'm going to skip oversaturated type applications because I want to stress what happens when you add quick look to this. Look, the only thing that changes when you add quick look to this setup is that when I'm instantiating a function type, look, so here in turnstile I, in this IArg rule, I'm saying the first argument here, E, is a value argument. The type of the function is sigma1 arrow sigma2. And what am I going to do? I'm going to take a quick look at the function by saying, look at E, that's this arrow judgment, look at E, with the expected type sigma1, that's the type filled with instantiation variables coming from the function, to produce a substitution theta1, that is what the quick look has learned from the first, well, from E. That's what it learns from E. And then I apply that substitution. Okay, and then let's see. Oh, I have to say, oh, I love this question from Mario. Why did you need so long to come up with this? Excellent question. One of the reviewers said, why did it take us so long to come up with this very simple idea? I have no idea. Just suffice it to say that it did. So it would be, for me, it's a huge success if, having written a paper, everybody says, but wasn't that obvious all along? Well, plainly, it wasn't completely obvious, or people would have written papers about it earlier. But if the result is easy to understand, that's a huge win. So thank you. Now, let's see. I think I'm going to leave the questions for now and just give a quick roadmap for the rest of the implementation, so that and then return to the questions. Let's see. But the thing I want to stress from these slides is how little changes in the de Clowto system. This gray box is one change. It has this auxiliary judgment, this lightning bolt thing. And what does it do? It looks at the argument application, h pi, and uses the same int judgment recursively, and then takes an ordinary most general unifier to do the quick look matching. And so it's extremely simple. I'm really showing you everything here. There's the auxiliary judgment for quick looking at the head. I'm showing you that too. And the last new bit I need to show you is what changes in the app rule. Here is the application rule. The top line and the bottom line of premises is unchanged. The only thing that changes is this middle line, which is the thing that exploits the quick look on the result of the function call. So that corresponds. So in here, this bit on this slide is the quick look on the arguments. This bit on this slide is quick look on the result. And that's it. And I've shown you almost all the other judgments that are necessary as well. So there's really not much to do. It's surprisingly simple. Let's see. I'm not going to talk about argument independence. So this is a sort of final slide just to summarize the talk, and then we'll return to questions. So there is an implementation of this. You can actually try it out. Here's the branch if you want to try it out. If I'm honest, the thing that I most like about this is that it really was easy to implement. It fitted with everything else that GHC is doing. And that, for me personally, is a huge win. There is a lot of mileage gained from treating arrow as a guarding type constructor, and that is a change from GHC today, but it's actually one that is independently valuable. Indeed, the GHC steering committee has already adopted it for independent reasons, quite separate from quick look. And last thing, just to say, the thing I'm least happy about really is this business about quick looking deeply inside arguments. It seems a bit brutal, and maybe we'll figure out a better way of doing this, or maybe it's fine. I don't know. But I just want to again be clear. It's probably the least elegant piece of this whole piece of work. Let me look back at questions. I'm scrolling to the top for upvoted questions. Worries, love, when. What I remember, some worries about quick look impredicativity breaking a specific typing rule. I don't remember about that. So no, sorry, I don't remember. What happens if there's still unsolved constraints at the moment quick look happens? Solving these constraints would instantiate the type of one of those arguments. Remember, quick look is taking the quick look, how to say this. There may be unsolved constraints floating about but they're only going to, the general constraint solver, the unsolved constraints part, GHC's existing constraint solver, continues to work only with monotypes. When I said we don't need to make any changes to GHC's existing constraint solver, I meant it. It assumes monotypes. It'll only do, it'll never instantiate a unification variable with a polytype, and it continues not to do that. So quick look never needs to worry that a as yet unsolved unification variable might later turn out to be a polytype. That can't happen because unification variables never turn out to be polytypes. And the only instantiation variables can become polytypes, and they live only from their birth is at the beginning of quick look and their death is at the end of quick look for a single call. Other things that quick look can't solve, even if it feels even if it feels like it should. And is there an easy example? Actually, I don't really have any examples where you think, darn, that is totally obvious and quick look doesn't get it. So treat that as a challenge. I would love to know if there are. Would this add more time to type checking already type check programs, or only to those programs that previously weren't but are now well typed? It does potentially add more time to even to type correct programs that don't need quick look, because it will still take the quick look at the argument, but it doesn't know that quick look at the argument isn't necessary. So yes, it will, and we'll have to see whether that is painful. I don't think it will be, but that's to do with are we going to pay a heavy cost for looking inside arguments? A lot goes on in type inference anyway. Oh, and by the way, quite a lot of what happens in the quick look, maybe we'll discover during quick look that like take reverse and it's given a list of ints. Well, quick look might discover that kappa must be instantiated to int, and that's true anyway. So that will save the constraint solver from doing some work. So maybe quick look will actually mean the constraint solver has less to do later. So it's making forward progress. It's not just a waste of time. This window keeps scrolling to the bottom. Can we just memorize what we learned from recursive quick look? Yes, that's what I meant. When I said, could we amortize the quick look? I was meaning, could we run over the syntax tree, as it were, doing all the quick looking business and leave the results in the tree and then exploit them in a subsequent type inference pass? And that's very much like stratified type inference does that Francois and his colleagues did. It's a little trickier in GHC where we might want to have an inferred function whose inferred type, or we don't know the inferred types during this pre-pass over the tree, if the function we're calling has an inferred type. So that's a little tricky. I guess I'm going to just say future work. Yes, maybe amortizing it would be a good idea by memorizing, or maybe literally memorizing. Maybe. Is there a semantic interpretation of what quick look achieves, something similar to principal types for Damas-Milner? Well, there's some. If you look at the paper, you'll see there is some meta theory there. I don't quite know. I think I'm not really qualified to speak in a well-informed way about a semantic interpretation. I mean, from a semantic point of view, quick look is just about figuring out instantiations for functions. Once it's done, it's then in plain old system F. So the semantics is exactly as system F. There's nothing new semantically. It's only a question about type inference. Can fxy different? Yes. So yes. Christoph asked, can fx in brackets applied to y behave differently than f applied to x applied to y? Yes. No. It won't behave differently because when decomposing an application, we do silently look through brackets. parentheses. So parenthesizing applications to the left won't change it. David Duray says, this feels like a bidirectional approach, but instead of context information flowing from parents' syntax nodes to from the parents to the children, it flows from sibling syntax node, or is this unrelated to bidirectional approaches? It's sort of related, yes, because it is basically a bidirectional system. Remember, right back in my slide here, there's this up arrow and down arrow business. That's what's pushing type annotation supplied by the user down, and indeed the types supplied by higher rank functions pushing them down. And that's been, in GHC for years and years and years. Straightforward bidirectional type inference. Go back to the paper that connected it most closely with GHC. It was called Practical Type Inference for Higher Rank Types, but it goes back a lot further than that. But it is true here that information is flowing between sibling nodes. So I might learn something from, I might need to look at both, I might need to look at both arguments of F together to they both contribute to the instantiation of F. But remember, it's very local. And you take the particular call, you birth the instantiation variables, you do the quick look, you substitute out the instantiation variables, all done. Now you're back to normal. So it's it's very local. It doesn't have this pervasive bidirectional sense that bidirectional type checking does. How does this relate to a PLDI? FreezeML. Yes, yes, yes. So Sam and colleagues' FreezeML paper is another very interesting point in this design space. There, they explicitly annotate where to generalize, or rather where not to instantiate, with little angle brackets. So for quick look, we need no new term forms, right? We did not need to say angle brackets run st $, blah. We just said run st $, blah. I think in FreezeML, you'd have to say angle brackets run st or something. Or maybe, actually, we need to instantiate the outer level, but not the inner. I'm not even quite sure. So there's some level of term annotation. Now, we might find in practice that some level of term annotation was better. Maybe users would like it more. I don't know. But there's something attractive about saying in the places where it's blooming obvious, you don't have to put any annotation at all. But I think that it's a usability design question. I think both are pretty simple technically, pretty simple and modular technically. So I think we'll need to wait and see. Are error messages significantly more complicated? Asks Richard. I don't know. We'll have to see. I don't think so. As in my branch of GHC in which I've got this going, I've run the entirety of GHC's regression suite, which has thousands of regression tests that involve error messages, and they basically don't change. So if you're not using this stuff, it won't make your error messages worse. Sarah asks, is extending this so it can deal with cases such as let, blah, 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 example, something I'm considering to do following down the line following an initial release? Or is there something inherently objectionable? Sarah, no, I don't think it's inherently objectionable. I just think that it's difficult to know where to stop. We could allow let, but then there are a lot of, if you look at Haskell's source syntax, particularly GHC source syntax, there are dozens and dozens and dozens of syntax forms. So we'd have to, as it were, write a new typing form for, a new case for each of those. So I don't think it's inherently objectionable, but I don't think it's, my instinct is, for what it's worth, is that the payoff is low. That is, I can't remember ever seeing a Haskell program in which somebody wrote a let expression in the function position of an application. I just have never seen it. But I may be proved wrong. And people write the most amazing Haskell programs, but I think we should be guided by where the shoe pinches in practice rather than by what is technically possible. Will this be in general GHC or hidden behind an extension? I think it will be hidden behind an extension for the foreseeable future. Yeah, pretty much everything else in GHC is hidden behind an extension. So I think this will be too. It'll be X impredicative types. Fritz, how is this related to Kafuri, Wells and co? Now as far as I remember, Joe Wells and Kafuri were trying to do type inference essentially for system F or for some fragment of system F. And I couldn't tell you. I think they need a more powerful form of unification. Is quick look plus unification related to a form of semi-unification? I don't know. I don't know. But I will say that for me, it's massively helpful to say everything else unchanged, right? So to change GHC's constraint solver to do semi-unification or higher order unification would be huge, right? To just say, change these a couple of hundred lines of code in one place, much easier. So, but reasonable question. The trouble is this is a complicated design space. Why is this sometimes fragile, quick look, so important that it's worth losing the more robust subsumption rules we used to have? David Fuhrer asks. Okay, so David, just maybe you could be more explicit about the more robust subsumption rules that you wanted to keep. I'm not sure we lose anything. Go ahead.
I think we've run a little bit over time, so we should probably draw this to a close now.
Yeah, yeah. I was just working down the list, but I'm very happy to draw to a close. Let me restart video so I can wave to everybody. Really sorry that if it was my network connection was causing bad stuff at the beginning.
I doubt that. So thank you very much, Simon. It's been great. I think I'm going to clap.
Thank you.
And just remind everybody that we have Benjamin Pierce speaking next week at the same time. So we hope to see you all again on next Monday.
Yeah, and do let me add a huge thank you to co-authors who did most of the heavy lifting on this stuff, Alejandro and Dimitrios and Yurian, and to John and Kun and Mara for organising all this. It's been fun. And it really, this will be in a GHC coming to you very shortly. I think the subject of a GHC proposal. It's a paper at ICFP.
Cool.
Good.
Thank you.
Okay. Thanks a lot.
Goodbye, everybody.
Bye. Cheerio.